All right, so we're gonna tackle this transistor calculation here, and what I got are the values that we know written into the circuit. So we have 12 volt source, we have a 10-volt drop across the. This would be our emitter, and this would be our collector. We've got 1.2 kilo ohm resistor on the base, and we have a current of 0.471 amps going through the collector. And what we need to know is the current going through the base, the resistance of the collector resistor, so this one here, and we need to know the voltage drop across the base resistor, this here, as well as beta. So we don't know exactly what beta is, our multiplier, our amplifier value from the current going into the base to the collector. That is something we're going to have to try to figure out. Okay, so one thing to take note of before we get started is the polarity. So we got the negative of our source on that side and the positive on that side there. And we'll notice that the negative, the current flow then, is going to be flowing into the emitter, into the N-type material of the transistor. So we know because the arrow is pointed out that this is an NPN transistor. And so for a transistor to be hooked up properly, the N needs to be hooked up to the negative. The N of the emitter needs to be hooked up to the negative. So this needs to be negative on this side, which it is. So it's forward bias. This transistor is going to work in our case. The second thing we need to know is that if we have a 10-volt drop across the emitter and the collector, you can think of the emitter, between the emitter and the collector, as being a resistor. It's going to restrict, there's going to be a voltage drop on it. And this emitter and the collector voltage drop is in series with this resistor up here. Therefore, Kirchhoff's voltage law states that the 12 volts needs to equal, the 12 volt rise at the source needs to equal the drops. So we got a 10 volt drop here. That must mean we have a 2 volt drop across our collector resistor. Another thing I want you to make sure that you recognize is this. So a transistor, between the emitter and a collector, you can think of it as a switch. Okay? So you'd have the emitter on one side, the collector on the other side, and the switch might be open. Now, if the switch is open and it's connected to, let's say, 12 volts, what potential difference is there going to be between the emitter and the collector? There is going to be 12 volts across it. Because the difference between this side here connected to the 12 volt source and this side here connected to ground, or the other side of the 12 volt source, is going to be a difference of 12 volts. That's what you get on across an open switch. In contrast, if you have a closed switch, and again we can imagine that's the emitter and that's a collector connected to 12 volts. Well, if you took a measurement of the difference in potential across it, you would read 0 volts. There's no potential difference now that the switch is closed. Now, transistor works a little bit differently. It's almost like a rheostat. So you can have, in some situations, let's get out of that. potentially have the switch halfway closed. And so if it's halfway closed, and we can think of it as like sort of like a resistor now, you would have in a 12 volt source, you would have 6 volts across it. So depending on how open or closed that switch is across the emitter and the collector of our transistor, it's going to affect the voltage drop across it. The more open it is, the higher the voltage drop. So if it's fully open, if there's no current going through the base to trigger the transistor in the first place, well, you're going to see all 12 volts across the emitter and the collector. If it's fully saturated, then you're going to see essentially 0 volts. In a saturated circuit, we assume that there's still 0.1 volts across it. Okay, hopefully that clears a few things up. But either way, if we know in this case that the transistor is open a little bit, and so therefore we got a 10 volt drop here, and we need to assume that the leftover voltage is 2 across that the resistor on the collector. Okay, so using Ohm's law now, we know the voltage here and we know the current. So we can take 2 divided by 0.471. That's going to give us a resistive value then of 4.25 ohms. So most equations again they boil back to knowing Ohm's law and knowing Kirchhoff's voltage and current laws. If you know those, then you can usually piece together an equation. Oh, I'm sorry. This is for this one here. So we know that the resistor value is 4.25 ohms across the collector. Okay. Now, another thing we can assume here with our transistor, whenever a transistor is activated, we know that there is going to be a 0.7 volt drop across our emitter and our base. And that's because a transistor is made up of diodes, pretty much. So to trigger a forward bias diode, you need a potential of over 0.7 volts, assuming that that transistor is a silicon transistor. That diode is silicon diode. So once you get the 0.7 volts, well, we know that this drop between the emitter and the base is in series with the resistor on the base. And so they need to equate to the 12 volts as well. So 12 minus 0.7 is going to leave us with 11.3 volts across our base resistor. Now that we know voltage and resistance, we can figure out the current. So we got 11.3 divided by 1200. That's going to give us 9.42 milliamps going through our base. And we can fill that in. 9.42 milliamps. We know that the voltage on the base, we figured that out. It's 11.3. All we got to do now is figure out beta. Okay, so remember that beta is a ratio. Beta equals the current on the collector over the current in the base. Oops. So in this case, we don't know what beta is. Beta is equal to, well, the current in the collector, which is 0.471, over the current in the base, which is 0.00942. Don't forget to convert the milliamps into amps. And that is going to give us 50. So our current in the collector is 50 times. It gets amplified 50 times compared to the current going into the base. And that's engineered right into the transistor. Okay. Now what I want us to do is to assume that the transistor now has become saturated. Okay? And so to saturate a transistor, we need to have the maximum amperage going across our collector to bring the voltage drop to as close to 12 volts as we can, meaning that the majority of that voltage drop is now across this resistor. If the majority of the voltage drop is across that resistor, then there's going to be hardly any voltage drop across the transistor at that point. So when the voltage drop between the emitter and the collector becomes 0.1, that's when you can no longer cram any more current into our collector. So let's take a look at that and solve for a saturated circuit. So a lot of these values now are going to become obsolete. What's going to stay the same is our voltage source. This resistance is going to stay the same. The resistor is fixed. We're going to assume then that this resistor is a rheostat, so it's variable, and we can change it. So this resistance is going to be different. Our voltage across this resistor is going to be the same because it's dictated by this 0.7 volts. But because the resistance is going to be different, the amps could be different. And this voltage is going to be different here. Our resistance is going to be the same. We'll clean this up a little bit here. This voltage drop is going to be different. Get rid of some of this too. Okay, so again, saturation is more or less that this switch has been fully closed between the collector and the emitter. But you're never going to get 0 volts like you do in this switch here, this one here. You're always going to have a little bit of voltage drop, and we assume that saturation will leave us with 0.1 volts here. Okay? If you have 0.1 volts there, that's going to leave us again because between the emitter and the collector and this resistor is in series. That's going to leave us with 11.9 volts here. Okay, if we know that's 11.9 and we know the resistance is 4.25, then we can determine that the current in saturated state is going to be 2.8 amps. So you cannot put any more current on this transistor collector. We can put more current on the base here, but that's no longer going to amplify and change our collector. It's saturated. Okay, another value that we can use from our previous equation is beta. Beta is not going to change. That's engineered into the transistor as well. So we have 2.8 amps on the collector, and we can use this formula again. Beta equals current collector divided by current on the base. We know that beta is 50. We know that current is 2.8, and we're looking for the current in the base. Now we just switch these values here to transpose the formula. So then we're left with IB equals 2.8 divided by 50. And now IB is going to be, let's see here, 2.8 divided by 50 equals 56 milliamps. So we can put in that information. Now what we're looking for here is the resistive value of this rheostat to saturate the circuit. Now that we have our voltage of 11.3 and we got our current of 0.056 amps, we can determine that this resistor needs to be approximately 202 ohms. And that is how you solve for a saturated situation. Hope this helps. And yeah, good luck.